Welcome, everybody. I have a few new topics today. I'm going to start with the first hour. I'm going to talk about a data structure called a DisJoint sets data structure. And then for the second hour, I'm going to come back to some miscellaneous topics in sorting. So let me start with DisJoint sets. A DisJoint sets data structure is a data structure that represents not one set, like in Homework 5, but a bunch of sets. But they have a relationship to each other, which is that they're disjoint. And what that means is that no item is in more than one set. So that's what the word disjoint means. And actually in a disjoint sets data structure, every item is in exactly one set. The collection of disjoint sets is called a partition. Partition is also a verb. We say that we partition a bunch of items into a bunch of different sets. Like at your local school, they partition the kids into the first grade, the second grade, the third grade, and so on. And we will have a universe of items. And what the universe means is it's all of the items that can be a member of a set. Again, every item is in exactly one set. So suppose, for instance, that the items in our universe are corporations that either exist today or used to exist, and that the sets are conglomerates that were created by merging corporations together. Then you would have an item called Microsoft, and you would have an item called Web TV. And because Microsoft acquired Web TV and the two corporations became one, they would both be in a set, which is also called Microsoft. And likewise, we're going to add some other airlines to that in a few minutes. But before I give an example, I want to talk about the operations that we want to be able to do on disjoint sets. There are two operations, just two, that we really care about, or that we really care about doing fast. You can add the other operations, but they might be a lot slower. The two important operations on a disjoint set are the union operation, which merges two sets into one. And the second is called a find query. And when you do a find query, you ask a question like, what corporation does Web TV belong to today? And the answer to that is, it belongs to Microsoft. So a find query takes an item as input and then returns the identity of the set that contains that item. Pardon me. We are not going to support operations that break up big sets into smaller sets, or at least we're not going to support them quickly. We can support them in linear time. But these are the two that we care about the most. And a data structure that supports these two operations quickly is sometimes called a partition, but more often people call it a union find data structure. There are a couple of applications of this particular data structure that you will see in the coming weeks. One of them will be in the homework that I'll release tonight, homework 9, where you'll see that you can use union-find data structures to create a maze. And the other one is in Project 3, which is already available for those of you who haven't noticed. Project 3 is out, and you're going to be implementing Kruskal's algorithm, among other things. You'll recall that in Kruskal's algorithm, there is a step where you need to figure out, as quickly as possible, whether or not two nodes in the graph are already connected by a path. What's the fastest way to figure out if two nodes in a graph are already connected by a path? It's actually to use a union-find data structure. So let's see how we do that. So let me draw an example of a universe of items that might interest us. I'm going to draw the names of some old airline companies which mostly used to exist, and one still exists today. And each of these is going to be an item in my universe of items. And I'll throw in a few other corporations that are not airlines. And so my union-find data structure looks like this. I have a bunch of items. Initially, every item is in its own set, all by itself. But then we can start merging them into bigger sets with the union operation. So as it happens, many years ago, Piedmont Air acquired Empire Air, and the two companies merged into one corporation. Likewise, US Air acquired Pacific Southwest, and Microsoft acquired Web TV. So we can model those with union operations. Before we do that, if I just take this input and I say find Empire Air, that find operation looks and tells me what set concurrently contains Empire Air. And let's just suppose that when we start, we're going to name each set after the one item that's in that set. So that find operation will return the item Empire Air is in a set called Empire Air. After I do that find operation, now suppose I do some union operations. So Piedmont Air takes over Empire Air, and these two get united into one set. US Air takes over Pacific Southwest, and they get united into one set. Microsoft takes over Web TV, and they get united into one set. And when you do this uniting, if you want, you can assign these sets any name you want. But when Piedmont Air took over Empire Air, the corporate masters decided to call the conglomerate Piedmont Air. So now that I've done this union operation, if I do a find on Empire Air, exactly the same operation I did before, now it's going to return a different answer. It's going to say, I am part of a hive mind called Piedmont Air. And then later on, you can do another union operation, because as it happens, years ago, US Air did take over Piedmont Air. And so these four companies all got merged into one big company called US Air. So today, if you do find Empire Air, well, it's still there in US Air. And when Microsoft takes over US Air, everything will be in one corporation and no further mergers will be possible. So now you know what this data structure is supposed to do. How do you do that, and how do you do it fast? If I asked you to just sit down and think of a data structure that does this, you would probably come up with the following idea. We're going to briefly look at what are called list-based disjoint sets. and something called the quick find algorithm. And by the way, here I'm using the word algorithm loosely to mean not just the algorithm that does find, but the algorithm that does union as well. So both algorithms are actually encompassed in this algorithm. The idea of list-based disjoint sets is for each set, you just keep a list of all the items in that set. And for each item, you just keep a pointer back to the list that contains it. So this is the totally obvious thing to do. All right, easy peasy. So an obvious advantage of doing things this way is that if you want to do a find, if you want to say, here's an item, what set is it in, it's very, very fast. You just look at the reference that each item stores, because each item knows which sets it's in. So find operations take constant time. And for that matter, the constant is really small. Union operations are comparatively quite slow. And the reason is, if you have two big sets of objects and you decide to unite them into one set, then you have to go through one of the old sets and relabel every item in that set so it points to the new set. You have to change all the references in all those items. And it's linear time, but still, it turns out we can do a lot better. So this is the obvious algorithm. It works all right, but actually it's a lot slower than what's possible, believe it or not. Union find is an example of an algorithmic problem where doing things in the obvious, easy way is not actually the fastest way to do things, and it's not actually even close. There is a much less obvious data structure that will do all of this much faster. Before I go on to that next data structure, though, are there any questions so far on how disjoint sets work or what this easy algorithm is? I'm not going to talk too much about the easy algorithm because the fast algorithm is much more interesting, but also because your TAs will talk about this in discussion section next week. So I want to move on to the fast algorithm, which is a lot less obvious. This algorithm is going to be based on trees instead of lists. We're going to make up trees to represent each set. And this algorithm is going to be called the quick union algorithm, as contrasted with the quick find algorithm. Because with this more sophisticated algorithm, union operations are going to be fast. They're going to take constant time. But find operations are going to be a little bit slower. They're actually not going to take constant time. So find operations are now slower than constant time, and they're now slower than they were in the quick find algorithm, but not much slower. We'll see. First, let me describe the algorithm, but just the The bottom line of all of this is that the quick union is faster overall, sometimes much faster overall than the quick find algorithm. So, as I said before, each set, now we're going to store it as a tree. And this is not a binary tree. This is a tree where each parent can have any number of children. One node, one item might have 1 million children. The data structure as a whole, therefore, is a forest. Remember from my lecture on Kruskal's algorithm that a forest is a collection of trees. We're going to have one tree for each set in our DisJoint sets data structure. So a forest of trees, one tree for each set. And each item, when you first construct a DisJoint sets data structure, each item is initially the root of its own tree. So when we get started, you have a bunch of items. Each item is in its own set, all by its lonesome. And then we can start doing union operations and putting these nodes together into bigger and bigger trees. One thing about this data structure that's interesting is that it's actually pretty much the simplest tree data structure you can use, because no node in the tree has to keep track of its children or its siblings. A node only has to know its parent, that's all. It does not refer to a specific data structure. Any data structure you can imagine that can store a set of general trees, you invent it, you can use it for this purpose. I will show you one particular data structure soon that's very fast, but by no means are you limited to using the particular data structure that I'll show you soon. Any data structure that represents a bunch of trees that can have any number of children will work, as long as it has parent references, because you need those to be fast. So you can have child and sibling references if you want to, but we don't need them, because the only thing we're going to do in this data structure is walk up the tree. The goal of this data structure is, if you give me a node, I want to be able to find the root of the tree. That's it. So to do that, all I need are parent references, so I can walk up the tree and find the root. Because the root is where I'm going to record the identity of each set. In other words, if I put Microsoft and Web TV together into one set, and I call the new set Microsoft, then I record at the root that the new set is called Microsoft. If I put them together and I call the new union Dumbcore, then I record at the root that the new corporation is called Dumbcore. Whatever, any name I want, I can stick it at the root and say that's the name of the set. And now, having done that, here's how we do a union operation. We make the root of one set become a child of the root of the other set. So here's an example. Suppose I've got my airlines sitting around. There's Piedmont Air. There's Empire Air. There's US Air. There's Pacific Southwest. Initially, each one is a set all by itself. But I want to take the union of Empire Air with Piedmont Air. So what do? I take the Empire Air tree's root and I make it become a child of the root of Piedmont Air. Now remember, I'm only doing parent pointers here, so that arrow there is pointing from a child to its parent. Piedmont Air is now the parent of Empire Air, and that means they're in one set together, and whatever that set is called, I store its name at the root, which is Piedmont Air. Again, I do another union operation, and I unite Pacific Southwest with US Air. Each one of them is their own one-node tree, so I make US Air become the parent of Pacific Southwest, and now I have a tree with two nodes representing one set, which is the union of those two airlines. And now suppose I take the union of Piedmont Air with US Air. So I want to unite all of these into one set now. Then I pick one of them arbitrarily, and I make it point at the other one as its parent. So if Piedmont Air decides that US Air is its parent, now US Air is the root of a tree with 4 items in it. If I want to find the set that contains Empire Air, then the way I do it is I walk up the tree. So I assume that I have some sort of reference to Empire Air, and then I can follow those pointers until I get to the root of the tree, which is US Air, and US Air will store the name of the set that contains all 4 of these items. So that is how you do a find operation. So how expensive is a find operation? It depends on the depth of the node in the tree. So in this example, if I do a find on Empire Air, then again, I have to walk up one step to get to Piedmont Air, and then I have to walk up another step to get to US Air. So in that case, Empire Air has a depth of 2, and the cost of doing a find operation is walking those 2 steps up the tree, plus a constant amount of extra time to look up the name of the set. So if you get a tree that's really deep, that's bad, because that means your find operations will be really slow. Our goal now is going to be to keep our trees as shallow as possible so that find operations are fast. Yes? How do you what?
How do you prevent if one data set has US Air already and the other set also has a different US Air, so they're both US Air, and then one takes the other, then doesn't the union not work because then there are 2 US Airs?
So the question is, suppose you have 2 different sets that both have US Air in them and you take the union, what happens? So I'm going to come back to, this is called a DisJoint set data structure, because we're only going to allow US error to be in one set at any given time. And if indeed there were two different sets that had US error in them, this would just be the wrong data structure and it won't work. So in that case, you don't use this one. You use something like the set data structure we programmed for homework 5. Mm-hmm. So just to finish what I was saying about this, again, the cost of a find operation is proportional to the depth of the item that we call find on. And so we want to keep that depth as small as possible. Are there any other questions on the basic union and find operations? Mm-hmm. Yeah, absolutely. So if USAir wants to store identity for the set and an identity for itself, that's not a problem at all. You just have an extra pointer in each node. So for instance, USAir, I've just drawn this node here, this USAir node, as just a circle with a name in it. But what it might really look like is something like an object that has an item name, which is a string saying US Air, and it might also have a set name field, which, in this case, if you wanted to name the conglomerate DumCore, then you can name it DumCore. And also, it has a parent pointer, but if this is the root, then the parent pointer is null. So that's what the item object might actually look like. And you can add more fields too if you need them. Other questions? Mm-hmm. The parents don't know what their children are, right? Is that the whole question? Yeah. So there's never a time when we need to know what the children are of any given node in this particular case. If you wanted to add more functionality to the DisJoint data structure, that might change. You might have circumstances where you want to add more operations that would need child pointers. And if you want that, you can have it. But for the basic union and find operations, we don't need anything but parent pointers. Sorry, can you talk a little louder, please? Mm-hmm. Yeah, there's a 2, 3, 4 tree does not support this at all for many reasons. One being that a node could have any number of children here, like 1,000 children. One being that this is not, in general, going to be a balanced tree at all. But is that your whole question, or is there more? Okay. Yeah. Yeah, so the 2, 3, 4 tree is totally unsuitable mismatch to this. All right, so what I've told you so far are the basic union algorithm and the basic find algorithm. What I want to talk about next are optimizations to those algorithms that help keep the depths of the trees smaller so that find operations will be faster. And there's 2 optimizations we're going to study. One of them is called union by size. The other one is called path compression. When you use both of those optimizations together, they're going to have a big, big influence on the running time of find operations. They're going to make them really fast. So let me start with the first one. The first optimization is called union by size. The observation here is that when I have 2 sets and I make one of them one of them have their root node become a child of the other one's root node, it doesn't really matter which one becomes the child set and which one stays the root node. I have two choices I can make. And so what I'm going to do is I'm always going to have the bigger set, that one's root is going to stay the root. The smaller set, its root is going to become a child of the root of the bigger set. And the reason to do that is, as your TAs will show you in discussion section, this keeps the items from getting too deep in the tree. You can't get long chains like trees that go doot, 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 doot. You can't get that. To do union by size, each tree has to know how big it is. So we're going to have a rule that at each root, we record the size of its tree. And by size, I mean the number of items in that set, the number of nodes in that tree. So that means our little data structure for an item here now also needs a size field, so we know how many items are in that particular tree. Once we've got that, then whenever we unite two sets together, we can look at the size of each set, take the one that's smaller and make its root be the child of the root of the set that's bigger. If there's a tie, you just break the tie arbitrarily. It doesn't matter. The effect of this is that trees will, the height of a tree can only grow logarithmically in the number of items. And I'm not going to show you that now, but your TAs will show you why in discussion section next week. Any questions about union by size? Mm-hmm. So the answer is yes, it is possible. The question was, is it possible that you have two trees and this tree is the bigger one, but the other tree is the deeper one? Yes, that absolutely is possible, and it does happen. So using the size to estimate the height is not perfect, but the thing is that we can record the size very quickly. What we cannot do with this data structure is actually figure out what the height of the tree is quickly. For reasons that will become apparent soon, you can't keep track of the height of these trees without spending a lot of time. So since keeping track of the heights of the trees is going to be just too expensive, we're not going to do that. We're going to use the sizes instead as a proxy, as sort of an estimate of how deep the tree could be. And sometimes it's wrong. Sometimes the tree is less deep than the logarithm of the size, but that's okay. That doesn't hurt us. It just means that our bound on the running time will be an overestimate. So we're good. Other questions? All right, before I go on to the second optimization, I want to talk a little bit about one very slick way to implement DisJoint sets that makes them just murderously fast. And before the lecture is over, I will give you complete and working code for a whole disjoint set's data structure, and hopefully you'll be impressed by how short it is. So what I'm going to do to make this simple is I'm going to assume that the items are numbered from 0 so that we can just use an array to look them up quickly. So either the items are a sequence of integers numbered from 0, or we have some way of mapping each item to a unique number, like a hash table, so that we can just use the number to look up the status of an item in an array. And this array is going to record each item's parent. But we're not just going to use the array for that, because some items do not have a parent. Those happen to be the items that are the roots of the trees, where we want to store the size of the tree so we can do union by size. So I'm going to store the sizes in the same array. If an item has no parent, then we will record the size of its tree instead of recording its non-existent parent. Now this is a bit of a kludge. I'm using one array to store two different kinds of things that are totally unrelated. Some array entries are going to store the parent index. Some array entries are going to store the size of the tree. I need a way to tell them apart. I need a way to tell which nodes are roots and which ones are not. So to do that, whenever I store the size of a tree, I'm going to store it as a negative number. So then whenever I see a negative number in the array, I will know that that means that that index is a root of a tree. And whenever I see a non-negative number, 0 or higher, in the array, I'll know that that item is not a root, that it's pointing at its parent. So here is what this disjoint set's data structure will look like when I first construct it, and every item is the root of its own tree. All right, so here's a brand new, freshly constructed disjoint set's data structure that has 10 items in it. Each item is in its own set, so each item is the root of its own tree, a tree of size 1. So every array entry is a -1, which means I am the root of a tree of size 1. So that's not a very interesting example, so let's go on to a more interesting example. Let's look at this forest here. So now I've done some union operations, and I've taken all these items and I've put them together into 3 sets. And by the way, you can't get that set on the left if you're using union by size. So just for the moment, let's suppose I did not use union by size and I got that tree. Just for reference, just for an example. So now the array will look like this. So let's start from the left. The parent of 4 is 5, So in box 4, we will put a 5. The parent of 5 is 8, so in box 5, there is an 8. The parent of 7 is 3. The parent of 3 is 8. And 8 is a root, so in 8's box, we don't store a parent. It doesn't have one. Instead, we store the size of its tree, which is 5, and we store it as a negative number so that we know that 8 is a root. Nodes 9, 0, and 6, their parents are all 1. And 1 is the root of a tree of size 3, so we store a negative 3 in its box. And node 2 is still a tree of size 1 all by its lonesome, so there's a minus 1 still in its box. That's what our array-based disjoint set data structure will look like for that particular forest. Yes? If your objects are strings, then I would recommend using a hash table to map each string to a number in the range from 0 to n minus 1. And in fact, you're going to do that for project 3. Yes? Oh, yeah, you're right. Sorry about that. I can't count. Pardon me, that should have been a minus 4, not a minus 3. Other questions? Mm-hmm. Okay, so if you need to store actual objects, which sometimes you don't, but the question is, once you get to the root of a tree, how do I get to actual objects? How do I get to, say, the name of the corporation? The answer to that is you just have a second array. So suppose I want to give each set a name. Now I'm going to have a second array, and if you want to get to objects, then you make a second array of objects. So once you get to the root of the set on the left, you're at the 8, you know it's a root. Now you can use this other array to get to whatever object will tell you, say, the name of that set, or whatever other information you want to associate with that set, which could be anything. And similarly, every root will have one of those. Other questions? Mm-hmm. You don't have collisions in this data structure. It's So what you have to do is you have to make sure that you have some way of assigning each string a unique number that's different from all the other strings. So like you have a counter, and whenever you encounter a string that you haven't seen before, you assign it the counter number and you increase the counter so that the next string will get a new unique number. You use a hash table to remember the numbers of the strings that you've already seen. And that way, when you hit a string that you've already seen before, the hash table will tell you what its correct number is. And if you hit a string that you haven't seen before, you can just assign it a new number. Mm-hmm. Well, if you're going to use this array data structure and you want to be able to insert new items into the universe, then you have a couple of choices. One is make this array big, like bigger than the number of items you start with. And then you can just always add new items on the right end as you create them. Or you can resize the array, just like we resize a hash table. So you can always make this array bigger if you need more space. Other questions? These are good questions today. All right, so I want to give you the code for doing the union operation now for this array-based data structure. And I'm going to assume that the input is two integers that are both the indexes of the roots of two different trees that I want to unite. For instance, if I want to unite the tree with 8 as its root and the tree with 1 as its root, then I will call union 8, 1, or union 1, 8. The order doesn't really matter much. What we're going to do, again, is union by size, which means we need to figure out which of the two trees is bigger. And so I'm going to compare the sizes of the two trees. So here's an if statement that compares the sizes of the two trees. I need to remind you that we are storing the sizes of the trees as negative numbers. So if array root 2 is less than array root 1, that means that root 2 has a bigger tree, because it's a negative number, than root 1. So if this if statement is true, that means root 2 has the larger tree. And if it has the larger tree, then we're going to make root 1 point to root 2. But before we do that, we need to update the size of the tree at root 2. If you haven't seen this notation before, this plus equal, this is Java and C shorthand for array root 2 is equal to array root 2 plus array root 1. It takes the old value of array root 2 and adds array root 1 to it and then stores it back in array root 2. So what this is doing is it's adding the sizes of the two trees, and that's the new size of the tree rooted at root 2. And then we make root 1 point to root 2 as its new parent. And that's all you have to do to unite two trees together in that case, those two lines of code. If the if statement is false, then we're going to just reverse those two lines of code and make root 1 be the new root of the tree instead. And that's the union operation. Any questions about this code? Mm-hmm.
Well, yeah, so you're just changing the table then, right?
This is just changing a couple of entries in the array, that's all. Mm-hmm.
But you're not changing like the roots themselves?
The roots? Well, this is how you change the roots on the tree. So here, like these two lines of code, you have... The array is the only representation we have of a tree. So if this is root 2 here, and this is root 1 here, and root 2 is the root of a tree of size 3, and root 1 is the root of a tree of size 5, then what this line, 2 lines of code are going to do is the first line adds their sizes together and fixes root 1 so that now it says 8. Actually, it says -8 because these are really negative numbers. And then the second line of code replaces the size of the tree with a pointer that says root 2's parent is root 1. That's what those 2 lines of code do. And since the array is our only representation of the tree, that changes the tree. Other questions about this code? So now that we've seen how that works, I want to go on to the second optimization, which is called path compression. Path compression is done in the find method. So the find method is going to be just as simple as the union method, but it's not going to run in constant time. It's going to be recursive. What it does is it checks if we're at the root of the tree. If we're at the root of the tree, then we return the identity of the tree. Otherwise, we walk up the parent pointer and then recursively call find on that node. But here's the thing. Let's suppose your tree looks something like this. If I call find 7, what happens? Well, I start at the 7, I walk up to the 4, I walk up to the 1, I walk up to the 0. 0 is the root, and I return the answer. But suppose I do find 7 again. Then I do it all over again. I start at the 7, I walk up to the 4, I walk up to the 1, I walk up to the 0. Suppose I do find 7 again, and again, and again, and again. If someone keeps doing find 7 over and over again, and 7 is deep down in the tree, then I'm going to have to walk up that same path many, many times. And that could get really expensive. In order to make this data structure as cheap as possible, what I want to do is compress the path. And that means once I discover that if I do a find 7 and walk up, I wind up at 0, why not just make 0 be the new parent of 7 in the find operation? That way, if I do the find operation again later, the 7 will be right there, a child of the 0, and now it'll be faster. So the second time I do find 7, I don't have to walk through 4, walk through 1. All I have to do is just walk one step from 7 to its parent, 0, and I'm done. So that's the first idea of path compression, is if I find out that the root of my tree is 0, just make 0 be my parent. And that way I can skip all the middlemen. The second idea is, okay, if I'm going to do that to the 7, why don't I do it to the 4 and the 1 as well as I'm walking up the tree? As I walk from some deep node up some path to get to the root, why not compress everything along the way, make them all point to the same root? So now the 4 is also going to point to the 0. And the 1 will point to the 0, though it already did. And so after one find operation, where I do find 7, I have done path compression. So now the 7 points to the root, and the 4 points to the root. And notice that not only did that reduce the depth of 7 and 4, it also reduced the depth of 8 and 9. If I now do a find 8, it will take fewer steps to get to the root than it would have before. So this path compression is actually maybe saving time on a lot of future find operations. Yes? Mm-hmm. So the question is, Why not just have everything be flat from the beginning? Why not just have one parent and many children? And the reason for that is, if you do that, you go right back to the first algorithm that I talked about briefly, the list-based disjoint sets and the quick find algorithm, where the find is very fast because everybody knows it's set, but now how do you maintain that when you do a union operation? When you take the union of two sets, if you want to keep it flat, that means you have to walk through all the items in one of those sets and make its items point to the root of the other tree. That's actually really expensive. We would prefer to do this lazily and put that off as long as possible if we can, because that's slow. That'll be linear time. Mr. Green Shirt over here. This permanently changes the tree in the find method. So once I've done this find, the tree is forever modified. Question? Okay. If it comes back to you, let me know. Over here. This is not taking us back to the quick find structure because we do not have to go through all the nodes in the tree. We're only readjusting the pointers for the things that we have to traverse to do this find operation. The vast majority of the tree will remain untouched, but also it helps that this has indirect effects, like the fact that the 8 and 9 moved closer to the root, even though I didn't have to look at the 8 or 9 or their pointers at all. Mm-hmm. To some degree, yeah. If you happen to build a tree that's relatively deep, then a few find operations will usually make it shallower, and then the find operations will get very fast. Mm-hmm. Question now? Yes, exactly. Right. For this to work, you have to have some sort of array that maps the numbers to the nodes in some way. Mm-hmm. So that's the whole premise of the data structure, is that you assume that you can get a pointer into these tree nodes. Mm-hmm. Well, this is the recursive method, and you're going to backtrack. I'll write the code, so you'll see this right now. Here's the find code with path compression, and hopefully this will answer your question. So I'm going to do a find operation on node X. X is an int, the number of whichever one I want to do find on. And so the first thing I'm going to do is I'm going to check if X is a root, because if X is a root, I'm already done. And for now, I'm just going to assume that the name of every set is the name of its root. If you want to have some other name, you can change this line of code and it'll work. But just to keep things simple for now, there's our base case. If we are already at the root of the tree, we will just return the same item number, and we'll call that the name of the set for now. Otherwise, if this is not the root of a tree, then what I want to do is I want to call find recursively on my parent, and that will return a value, which is the root of the tree. And I will store that as my new parent immediately. So again, this is a really slick line of code. This line of code it figures out who my parent is, it calls find on my parent. That find will recursively go all the way to the root of the tree and return the identity of the root. After the recursion backtracks, now I know who the root of the tree is, and so I store that as my new parent. And then I return that value as well. So that is the find operation, and I hope that answers your question. I talked about this before briefly when I answered one question, but just a quick word on if you want to actually name the sets, the find code I just showed you, it just assumes that the name of each set is the same as the name of the root, which, if that's not adequate for you, then, as I said before, you want to have an additional array that maps roots to set names. So, for instance, if Microsoft and US Air have a merger, if we do union by size, then US Air is going to be the new root, because US Air had 4 items in that tree, but Microsoft only has 2. But you know that Microsoft's going to want to keep the company name Microsoft. So you use an extra array that maps the US Air node to the string Microsoft. And that reminds you what the real name of the set is. However, I want to mention that there are many applications where you don't actually care about naming sets. There are a lot of applications where all you care about is the question, I have 2 items, are they in the same set? And that is going to be the situation in both Project 3, in Kruskal's algorithm specifically, and in Homework 9. So, for instance, in Kruskal's algorithm, each DisJoint set is going to represent a connected component of the graph that you're building. And X and Y are in the same set if they're connected by a path in that graph. And so to answer that question, what you do is you run find on X and get the root of X's tree. You run find on Y and get the root of Y's trees. And then you just check if those 2 roots are the same. And if they are, yay. Now you know. And if they're not, then they're not in the same set. And if it's Kruskal's algorithm, that means you can connect X and Y with an edge. So I want to briefly tell you about the running time of quick union, even though it comes with a horribly complicated proof that you probably never want to see. First of all, again, as I said before, union operations obviously take theta 1 time. How do you know they take theta 1 time? Well, just look at the code that we wrote for them. If you look at this code, no loops, no recursion. It has to run in constant time if it has no loops and no recursion. On the other hand, find operations are a little more interesting. The worst case time for a find operation is theta log u, where u is the number of union operations that have been executed since you first created that DisJoint sets data structure. However, that's the worst case time. And your TA will show you why again in discussion section. But the average case time is actually better than that because of path compression. And so the average running time is not going to be the same as the worst case time. It's going to be close to a constant. It's going to be so close to constant that it's almost a theoretical technicality that it's not really a constant. But here is the bottom line. If you do a sequence of F find operations and U union operations, then the total running time for that is big theta of the number of union operations plus the number of find operations times this weird function, alpha of F plus U and U. That's going to be, that alpha is the average running time of a find operation. And that's the worst case running time. What is alpha? Alpha is an extremely slow growing function. And it is called the inverse Ackermann function. I'm not going to tell you how to define it, because we'd be here all day, but when I say that the inverse Ackermann function is extremely slow growing, I mean it's comically slow growing. It's one of these functions that mathematicians throw around to sort of give you pathological examples of just how slowly a function can grow. And essentially what that means is that this function is never greater than 4 for any values of f or u that you could ever do in a lifetime on one computer. Now, technically, in the limit as f and u go to infinity, so does the inverse Ackermann function. It just gets there so slowly that the universe will have reached heat death before it gets to 6. So, for all practical purposes, find operations run in average in constant time for all practical purposes, but not on the final exam. On the final exam, they're infinitesimally slower than constant time. Any questions about that? So that's it for DisJoint sets. Now I want to quickly go through 3 topics related to sorting. The first one is called selection. Suppose that you want to find the kth smallest item or key in a list. In other words, to put it a different way, you want to put the item that would be at index j if the list were sorted where j is k minus 1. So I want to find the kth smallest item for an arbitrary k in a list. The easy way to answer that question is sort the list. We know a bunch of sorting algorithms now, and just pick out the item at index k minus 1, and that'll be the kth smallest item. But can we do it faster? Can we do it faster than sorting? Sorting usually takes n log n time. We'd like to beat that. So if we don't want to do that, then this is a problem that is called selection, selecting the kth smallest key fast. And a really common example is finding the median of a set of n keys, in which case you're looking for keys. You're looking for the item whose index in the sorted array, if you had the sorted array, would be the floor of n over 2. This is something that comes up very commonly in statistics. You have a list of statistical data points. You want to compute the median. How do we do it fast? We're going to use an algorithm called quick-select, which is a modification of quicksort. So we take the quicksort algorithm as we've seen it, and we make some small changes. The most important change is that whereas quicksort calls itself recursively twice, quick-select will only call itself recursively once, either on the left partition or the right partition, but never both, and therefore it will be faster than quicksort. Quick-select is going to start exactly the same way quicksort does. You start with an unsorted list, which I will call I, of n input items. We will choose a random pivot from that list. We will partition that set I into 3 different lists, I1, IV, I2. Remember that we're doing this exactly the same way we did during the lecture on quicksort. So all of the keys that are less than the pivot go into list I1. All the keys greater than the pivot go into list I2. The pivot itself goes into this list IV. Keys that are equal to the pivot can go into any one of these 3 lists. Again, we're going to use the same methods we used in the quicksort lecture. So we'll do one thing for linked lists. We'll do a different thing for arrays. But this step is exactly the same as quicksort. Nothing has changed yet. So items with the same key as the pivot can go into any of the 3 lists, but the pivot itself has to go into IV. Now that we've finished the partitioning step, which is the hard part of quicksort, or at least the part that takes the most time, the only thing that changes is how we handle the ending. And at the ending, as I said, we're only going to call quick-select recursively at most once instead of twice. So what we do is we have these 3 lists. We figure out which of the 3 lists contains the index that we're looking for. So the first thing is figure out if it's in the first list. So the first list is called I1. This notation here means the cardinality of I1, the number of keys in that set I1. If index j is less than the number of keys in that set, then we know that that set is where we'll find the item with index j. And so we will call quick-select recursively on I1. And then we'll return that index. Well, we'll return the item, actually. Otherwise, if the index j is big enough that it's not in the first list, maybe it's in the middle list, the list of keys that are equal to the pivot, or at least the list that contains the pivot. So if the index is less than the length of the first 2 lists combined, then we look in the list IV, but everything in the list IV is equal to the pivot. So let's just return the pivot. If neither of those 2 cases are true, then there's a third case where j is bigger than that, and therefore the index that we're looking for has to be in the third list, of keys that are greater than the pivot. And so we recursively find the index in that list. And we have to adjust the index accordingly because the index will be different in the last list. And that is the code. Any questions on that last part? So again, the main insight here is that when you do quicksort, you have to recursively sort both halves of the partition. When you do quick select, you only have to look in one half of the partition, the half that contains the index that you're looking for. And that's going to make this faster than quicksort. In fact, we can prove, and I may have a chance to talk about it later in the semester, that if your random pivots are reasonably well chosen, then the average running time of this code is linear. By the way, this algorithm really is the code that virtually everybody uses in practice when they need to do median selection or other selection fast, because it really does work well and works fast. It's randomized, so all we can say is that it runs in linear time with very high probability, but that's generally good enough in practice. Any final questions on this? Yeah. What's the alternative algorithm? Oh, well, I mean, if you quicksort the entire list, it's pretty much always slower. So, I mean, the difference between quicksort and quick select is, when you do quicksort, you have even in relatively small examples, you'll have a tree that looks like this. If the index that you're looking for is here, then you don't have to sort this part, you don't have to sort this part. Quick select just does, except in the smallest examples, strictly less work than quicksort does. Sorry, louder? Well, then the question gets complicated. I don't know where the trade-off is there. You would want to experiment and find out. Next, I want to talk about the fact that comparison-based sorting algorithms, which are what we've been studying, are limited in how fast they can be. So mostly this semester we've concentrated on proving that algorithms run at least this fast. This is going to be different. This is going to be a proof that sorting algorithms run at least this slow. And not just a particular sorting algorithm, but a whole class of sorting algorithms called comparison-based sorts, which include every sort algorithm we've looked at so far. So, to get started, I need a little background before we can come to the main topic. If you have n numbers, and each of the numbers 1 through n occurs once. So, like if it's the numbers 1 to 5, maybe it's 5, 1, 3, 2, 4. And the question is, how many different ways are there to order the numbers 1, 2, 3, 4, 5? And those of you who've maybe taken some probability or some combinatorics class know that the answer is n factorial, which is written n with an exclamation mark, but mathematicians call this n factorial. And n factorial is official math notation for what you get when you multiply 1 times 2 times 3 times so on all the way up to n. Why is that the answer? Well, suppose you've got a hat and you fill it with all the numbers from 1 to n, and you draw numbers out randomly from your hat one by one. There is the very first number you draw out of your hat could be any one of n different possibilities. And so let's take one number out of my hat. There's n different choices, equally likely, and put that here. Then I reach into my hat again, and now I pull out the second number in the sequence. There are n minus 1 numbers left in the hat. I pull out one of them. It could be any one of those n minus 1 numbers with equal likelihood, and I put that in the second position. So there are n possibilities for the first number in the sequence. There are n times n minus 1 possibilities for the first 2 numbers in the sequence. For the first 3 numbers in the sequence, the number of possibilities is n times n minus 1 times n minus 2. And so on, I go through the rest of the numbers in the hat. Following this logic to its conclusion, the total number of possible orderings is n times n minus 1 times n minus 2 times n minus 3, all the way down to 1. Now, each of those n factorial different orders that we can choose is called a permutation. For example, 5, 3, 1, 2, 4 is a permutation of 1, 2, 3, 4, 5. There are n factorial possible permutations. And by the way, for homework 9, you're going to be asked to randomly create a permutation of n numbers for the purposes of making a random maze. So one thing I want to know is a rough estimate on how big n factorial can be, or more precisely, how big the logarithm of n factorial can be. So let's observe a few things about how big and how small n factorial is. So first of all, since it's equal to 1 times 2 times 3 times so on up to n, that is less than or equal to taking n and multiplying it by itself n times. So we know that n factorial cannot be bigger than n to the nth power. I want to have a lower bound as well. So what I'm going to do is I'm going to just pick out half of the terms. The terms starting with n over 2. And if I do that, then I discover that at least half of the terms that I'm multiplying together are equal to n over 2 or bigger. So if I multiply together n over 2 numbers that are all n over 2 or bigger, then their product is going to be bigger than n over 2 to the power of n over 2. So that gives me a lower bound on how big n factorial is. And now, what I really want to bound on is logarithm of n factorial. Well, that's less than or equal to the logarithm of n to the n, as we just saw. And it's greater than or equal to the logarithm of n over 2 to the power of n over 2. And so we can now take those logarithmic factors down. By using the standard identities for logarithms. And now we can see that logarithm of n factorial is between, well, it's between n log n as the upper bound, and as the lower bound, there is something that is big O, well, big theta of n over 2. Let me write it this way. So what this means, the bottom line, is that log of n factorial is in big omega of n log n. Sorry, big theta of n log n. We're going to use that fact in a few minutes. To see where we're going to get there, I need to define what a comparison-based sort is. A comparison-based sort is one where all decisions are based on comparing keys. And usually those comparisons of keys are done in if statements. So if you think of all the sorting algorithms we've looked at so far, what do? You know, quicksort, for instance, compares pairs of keys and swaps them if they're in the wrong order. Insertion sort more or less does the same thing. All of the actions that are taken by all of these sorting algorithms are based on a bunch of if statements which ask true or false questions and then make a decision where to go based on those true or false questions. So now what I want you to do is I want you to imagine that we have two different computers that are both running exactly the same sorting algorithm on two different inputs. And let's suppose that whenever one computer reaches an if statement and the other computer reaches the same if statement, if the first computer gets true, the second computer also gets true. And suppose whenever the first computer gets false, the second computer also gets false. That means that as the two computers run the same algorithm, they're always going to follow exactly the same path through the code. That means they're always going to do exactly the same data exchanges. If one computer swaps two numbers, the other computer will swap the numbers in the same two places. And therefore, the two computers will permute the input numbers in exactly the same way. So, if you want to have two different orderings of numbers, and you have a correct algorithm that sorts both those two different orderings of the same numbers, then at some point they have to have a different decision. One computer says this comparison is false, the other computer says, oh, from my data, that comparison is true. There has to be a different sequence of true and false answers for every possible permutation of the n input numbers. And that's the key point here, is that if a sorting algorithm is correct and actually works on every possible permutation of the input numbers, then it must generate a different sequence of true-false answers for each possible permutation of the input numbers. And if the algorithm asks a total of d questions, meaning that we go through d different if statements, and each one gives us a true or false answer. Then it can generate at most 2 to the power of d different sequences of true or false answers. But there has to be a different sequence of true or false answers for every possible permutation. And so that means that n factorial, the total number of possible permutations, has to be less than or equal to the number of different sequences of true-false answers we can get by asking d questions, which is at most 2 to the d. This inequality has to be true for any algorithm, any comparison-based algorithm that actually gives you the correct answer. And so if I take the logarithm of both sides of that, then I get, specifically the base 2 logarithm of n factorial is less than or equal to d. So the number of decisions that I have to make is at least log of n factorial, and we've already seen that that is in big omega of n log n. Now, to bring this back to running time, what's the algorithm's running time? Well, every time you do an if statement, that if statement takes constant time just to figure out the answer. And since we have to ask at least d different if statements to get the right answer, that means the algorithm spends at least omega d time asking those d questions. And it follows from that that every comparison-based sorting algorithm is going to require big omega of n log n time on at least some of its inputs. And that's the bottom line. And this is an amazing claim because it doesn't just analyze one particular algorithm like quicksort or heap sort. This is a statement that's true for all comparison-based sorting algorithms, including thousands of algorithms that nobody has even invented yet. This says there will never be, in the future, anyone inventing a comparison-based sorting algorithm that's faster than n log n. And that's kind of an amazing thing. Any questions about that? Mm-hmm.
When you say the sequence of true and false, is there an order? Because even if you get the same answer, depending on which two you're comparing, it might convert to a different permutation?
I'm sorry, I don't understand the question.
What is the number that you're comparing when you say that the true and false questions? Because like even with the same algorithm,
Mm-hmm.
the thing that is comparing this step might be different. So even if it gets the same true and false questions, that may refer to two different numbers. How do you know that that's the same permutation?
Well, think specifically if we have the numbers 1 through n, and we permute them in 2 different ways, and we give them to 2 different computers running the same algorithm. Because they are 2 different permutations of the numbers 1 through n, this computer is going to have to rearrange its numbers in a different way than this computer rearranges its numbers. So if they're going to rearrange their numbers in different ways, the only way to achieve that is one of the if statements is true here and false here. That's the only way. It doesn't matter as long as they're comparing two keys. All the conditions are if this key is greater than this key, if this key is less than this key, that kind of thing. We can talk more after the lecture if you like. So now that I've said that algorithms faster than n log n are basically impossible, let's talk about how to sort in linear time. There are algorithms that are faster than comparison-based algorithms because they don't just make two-way decisions. They make Q-way decisions. And you can choose Q to be relatively large. So in other words, we're not just relying on if statements anymore to affect the way that the algorithm behaves. We need a way to decide not between two options, but a way to decide between 100 options, all in constant time. And it turns out you can do that with array indices. So some of these algorithms that do this run in in linear time, and we'll learn 3 of those. The first one will be bucket sort. Bucket sort is kind of a limited sorting algorithm. We will fix that limitation on Monday. But for now, let's just think about how do we sort a bunch of numbers under the circumstance when the keys are distributed in a very small range. So for instance, let's suppose all of the keys that we want to sort are integers in the range 0 to q minus 1 for some number q that's not horribly large. Specifically, we will assume that the number of possible keys is in big O of the actual number of keys we want to sort. So how are we going to do that fast? We're going to do it with an array of q's. We are going to allocate an array of q's, and the number of q's will be q, and that means that there is a separate q for every possible key, every possible number that might come up while we're sorting. And so those q's will be numbered from 0 up to q minus 1, matching the keys. And the algorithm is you walk through the list of input items, and whenever you hit an item whose key is I, you put it into qi. So again, I'm just very simple algorithm. Just walk through all the keys, each key in turn, put it in the queue of the same number. Key I goes into qi. To give you an example of what this looks like, let's consider the following input. I'm going to give an example here where each item is a key and an associated value. So I'm sorting the numbers. The letters are just there to remind us that those numbers may be different from each other in terms of the data that's being carried along with the number. So let's sort these items. By the way, the values associated with these keys, I have put them in alphabetical order. It doesn't have to be in alphabetical order. I'm just doing that because I want to demonstrate the stability of this sort. So what the algorithm is going to do is it's going to build a bunch of queue fronts, one for each possible key. There are 8 possible keys from 0 to 7. And now we're going to go through that input list from left to right, and we're just going to take each item and we're going to put it on its queue. So the first input is 6A, so let's put that into Q6. So done with that one. The second item is 7B, so that'll go into Q7. Done with that one. Next is 3C. Done with that one. 0D. Done with that one. 3E. All right, notice that I'm always going to put new items at the end of the queue, not the beginning of the queue. These are not stacks, these are queues. And the reason why is I want this sort to be stable. Hopefully you remember from the homework what stable means. It means that if 2 items have the same key, they will be in the same order in the output as they were in the input. I go on to 1F, put 1F into Q1. 5G goes into Q5. 0H goes into Q0. 3I goes into Q3. And 7J goes into Q7. And let me just draw here as a reminder that while we're doing this, there is also a bunch of queue tails, because this is really an array of queues, which means that for each queue, there's a tail pointer that points to the last item in each of these queues, and that's what allows me to add a new item to the end of the queue in constant time. And when we're done, well, there were no 2s and 4s, so these references are still null. So now we're done the first part of bucket sort. We've put each key into its proper bucket. And now to get the output, we're just going to take all these linked queues and concatenate them together into one big queue. And that linked list will be our output. So one thing you'll notice again is that if keys came in a certain order in the input, like 3C, 3E, and 3I, then they're going to be in that same order in the output, 3C, 3E, 3I. Oh, one more thing. If this data structure looks to you like a hash table, it basically is pretty much exactly like a hash table, or a hash table with tail pointers anyway. It's a hash table where the hash code maps key I to bucket I, so the hash code is the identity function, and there is no compression function because we don't need to compress. Now the running time of this is theta and q plus n. And that is both worst case time and best case time. It takes theta of q time to initialize all the buckets and then to concatenate them all together at the end. It takes theta of n time to put all the items in their buckets. And there's no circumstance under which either of those is faster or slower than linear time. So again, theta q time to handle the buckets, initializing them in the beginning and concatenating them at the end. Between initializing and concatenating, it takes n time to put all the items in their buckets, because there's n items. And this is a big win if q is small, because if q is in big O of n, then the whole thing takes theta of n time, obviously. On the other hand, if q is much bigger than n, this isn't going to work, and I'll need to show you on Monday how to fix that. But the question is, how did we get around the n log n lower bound on comparison-based sorting? Well, this is not a comparison-based sort. We're not comparing two keys with each other and doing something based on one being bigger and one being smaller. Instead, we're just taking each item in turn, and we are making a QA choice, where I just decide which of the Qs I'm going to put the item on, and Q is a number much bigger than 2. I'm not making two-way decisions, I'm making 8-way decisions, and that's a win. And let me remind you, I've already said it a couple of times, but bucket sort is stable. And that's going to be really important on Monday when we use it to create radix sort. So come back on Monday and we will learn our last two sorts.